Welcome to a lesson with Dr. Powell. We are going to look at an optimization problem in calculus. We're going to try to find the angle theta that will produce the maximum pyramid according to some specifications. The base of the pyramid will have corners that touch the outside boundary of, or the inner boundary of the sphere in which the base is inscribed. The top of the pyramid will sit exactly 1 unit above the center of the sphere. And the radius of the sphere will be 2. According to these specifications, and also we want that the base, we need one more specification, the base is actually going to have a particular shape. The side lengths are going to be 2 to 1. So if I can draw that straight, here we go. Oh, come on. All right. The idea here. Okay, so twice as long as the other side. And it's going to depend on theta. So we want to maximize the volume of the pyramid, so we need to come up with a formula for the volume of the pyramid in terms of theta based upon the specifications. The specifications will actually allow us to write the volume as a function of just the angle theta. So volume of theta is what we're after. But first, let's just come up with a formula for V. Okay, thinking of different things. Realize that the radius 2, theta, d sit in this triangle. I'm going to put another variable here, lowercase t, to represent this side length right here in that triangle. And that's going to help us relate via Pythagorean theorem, or not even Pythagorean theorem. I mean, just the angle theta and trig functions are t and d together. Okay, so let's think about how we can write d. Okay, so if we had d, maybe is where we should go, how would we find the area of the base? Well, we know this is a 2 to 1 ratio. So 2 to 1 ratio means this side like 2 to 1. Hey, there's only one angle that can give that to us. And I'll call that phi, but it's actually going to be the inverse tangent of, this is 1 to 2, of 1 to 2, or the fraction 1/2. So it's fixed, and it's going to be the same for every single pyramid according to the specifications that we're using. Now, this side length, well, or this part of it right here, is actually going to be d cosine phi, and this one is d sine phi, using the idea that if you have a triangle with a 1 here, this side length by definition would be sine phi, this is cosine phi, and then if you multiply everything by something like d, that's what you'd get. Okay, so using that idea, we get that the area of the base is simply, let's see if we extend this down, that's 2. Extend this all the way across, that's 2. Area base is just 2, it's just this times this. So 4d squared times sine phi cosine phi, and this is the area of the base. Okay. Now, what about, so if that's the area of the base right here, 4d squared times sine phi times cosine phi, right, so sine phi times cosine phi, good. All right, then we need the height of the pyramid. The height of the pyramid is going to be 1 plus t, whatever t is. So 1 plus t, and we get t from, okay, and maybe we'll just write that in right now, 1 plus t, because we wrote d right here. Okay, so we have d. We have, now, sine phi, cosine phi, thinking about this is actually just, I mean, phi is a fixed number in this situation. As we're varying our pyramids according to the specification, phi will remain fixed. So this will remain fixed. So this is just constant, it can be ignored. This is constant, can be ignored if you want, because really we're just trying to find the angle that'll make a maximum. And if this is just a constant, in fact a positive constant, then it can be completely ignored as we're looking at derivatives and where they're equal to 0 and how they're behaving for maxes and mins. So we can just kind of ignore that, maybe swallow it up in a big constant, that 4 and that just as a constant k, say, all right? So k, so really we have k d squared 1 plus t, which is nice. Now we just write d in terms of what it is using this theta, because that was phi, now we're going to theta. Okay, so thinking of a triangle here, r is 2, and I'm going to put theta right here. What is adjacent to theta? It's t, right? What's opposite theta is d. So we can think of a triangle with a 1 theta, sine theta, cosine theta, multiply it by 2, 2, 2, 2, and see how these are similar to each other. To notice that d is 2 sine theta and t is 2 cosine theta. So d being 2 sine theta squared times some constant k, 1 plus, and then we have what t is, it's 2 cosine of theta. So this is, okay, so we can say this is v of theta where k is some constant. In fact, let's just, make like, a new constant, because we're going to get a 2 squared 4. Let's combine that with that to just make it like k tilde, say, new constant, times sine squared theta times 1 plus 2 cosine theta. And it's still the function. We haven't gotten a derivative yet. Let's perhaps do this a couple different ways. I guess we could multiply it through, or we could use the product rule now. I feel like using the product rule right now. In fact, I'm going to ignore this k tilde. It's just a constant in here. And let's just pretend like this is my function right here, because this k tilde as a positive constant, we can ignore it. So we get derivative of the first part is 2 sine theta using power rule, but then using chain rule, derivative of the inside sine. So this is sine theta quantity squared. So the inside is sine theta, derivative of that is cosine theta. Okay, times the 1 plus 2 cosine theta as is. Then plus, and then we're going to get sine squared theta as is times the derivative of this part. The 1 goes away, but then we left with negative 2 sine theta. Okay, so that's kind of, I guess if you said it was like, I guess if you put the k tilde back in, then that would be equal to v prime of theta. Okay, so we want to see where this is equal to 0. And, what I could do is I could multiply, maybe I'll do that. I'll just multiply this through. So I get, let's see, what is that? 2 sine theta, cosine theta, and then, I could either multiply it through right now or just put x's and y's everywhere. That's probably, I guess I could do either way. Maybe I'll just do, yeah, because I like to change all my sines to y's and my cosines to x's. So just think of that. 2yx 1 plus 2x plus y squared. And actually, but then, see this, we'll put that minus right here. So minus 2 times y cubed. Okay, because it's like sine is y and cosine is x. So we'll be left with 2xy plus 4 x squared y, 4x squared y, and then we get minus 2y cubed. Okay, so we have this. I want to see where this is equal to 0. And we know that in particular, since this x and y's represent cosine and sine, we're on the unit circle. So we which has the equation x squared plus y squared is 1, which is nice. Okay, so I'm going to factor out, so we're just basically finding an intersection point on there, and that helps us solve the trig function, or the trig equation. We factor out the y here, because it's factorable out by y. We're left with 2x plus 4x squared. In fact, we could factor out a 2 as well, right? We should just do that. Let's factor out a 2y. Let's factor out the 2y, and we're left with x plus 2x squared, and then we're left with factor to 2y's, so that would be a minus y squared to 0, right? Let's see if we factor out a 2y. Yeah, okay. So then in that particular case, all right, so we can, in fact, we can factor out we can continue, we can factor out a negative 2y, a negative, and rearrange this to be, actually, let's just, before we do that, see this y squared and this x squared? We can actually relate this y squared to x squared via this equation right here. Y squared is going to be equal to 1 minus x squared, and, or you can think negative y squared, if you move the negative y squared over, is equal to x squared minus 1, which is what we want. Negative y squared is equal to x squared minus 1. So we have x squared minus 1, 2x squared, and you have an x. Okay, and you have a 2y. Okay, so this part right here would become 3x squared plus x minus 1. Okay, so, and that's multiplied by 2y equaling 0. Okay, so then what we can do is we can figure out, so 2y equaling 0, that's when the sine of theta is equal to 0. If we restrict ourselves, in fact, let's just do this for simplicity, where theta has to range between down here, so between 0 and pi halves, or 0 and 90, or whatever you want to think of it, it has to be down here. And so really this will never, and strictly between, which means this will never be 0. So really we need to focus just on this part. When is this going to be equal to 0? What is, well, first of all, what are the x values that make this equal to 0? And that's going to be what cosine is equal to, because if you're on the unit circle, x is cosine at a coordinate point x, y here, and the y is the sine. So we're really just solving that equation. 3x squared plus x minus 1 equals 0. And if you use my technique, 3, 1 for quadratic equations. See, we drop down this little synthetic division diagram. I have a video on it, or you can just ignore and do it your own way if you want. Okay, but anyways, we drop a 3 here. You drop 1/2 of that. You take this guy, divide by that, and change its sign, so negative 6. Then take negative 6, multiply to that, negative 1/12. Then you add down right here, so negative 13 over 12. Then you take, so the result, so what is x equal to? So x is going to be equal to this guy, which is simply this divided by that, change sign, plus or minus the square root of, so remember how we took this divided by that, change sign? Now take this one divided by the front, 3. So that divided by 3, change sign. And that's what goes in the square root here. So divided by 3 just multiplies 3 to the denominator, so 36, and changing sign gets rid of that negative, so 13 over 36. Okay, so it looks like cosine is going to be equal to this, so we're interested to know cosine, so the cosine inverse of which one of these. Now we don't want the cosine of theta to be negative because of our specification, so let's look at the positive one. Positive one happens with the positive here, because the square root of 13 over this, I mean, that's like square root of 36 is 6, and square root of 13 is over 3. So, I mean, this part is over 1/2. And so negative 6 plus 1/2, yeah, you're going to be positive, and that looks like what we want. So it's going to be cosine inverse of negative 6 plus, and we can write it this way, square root of 13 over 6 Okay, and that's what theta should be equal to in order to get a maximum pyramid according to our specifications. Realize that that we never kind of the 2-to-1 ratio was kind of swallowed up in the constant k. It had nothing to do with what theta is. We could have just ignored it. But nonetheless, we just need to know that the base is some fixed constant times d squared. So we may as well just have said it was a square, but it just made it a little bit more interesting to think about. Anyways, so theta being this should yield that. Now, of course, how can we detect that it really yields a maximum? Suppose we could take this guy right here, take its derivative, find the second derivative, plug this guy in, and just make sure you're getting something positive. There have been some videos where we looked at that. I will refrain from that in this one. Hopefully that you've been able to glean something from this video that may help you. Thanks for watching.